Your mission is to send a spacecraft to the outer solar system on a limited budget of rocket fuel. And that's not all. The trip must take you less time than allowed by your fuel tank. Sounds like time travel? Crazy? Mind-boggling? Yes, indeed. But it is not mission impossible. My name is Bassem Sabra. I am an astrophysicist at NDU in Lebanon. Let's begin the challenge. Just to help you appreciate the seriousness of the challenge, a short intro into the long distances in the solar system is in order. The distance to our moon is a little bit less than 400,000 kilometers. The distance to the sun is about 150 million kilometers. The Saturn V rocket that took Apollo 11 to the moon was 3 million kilograms and took 3 days to reach there. What would you say if I tell you that to go to the planet Saturn in less time than what is allowed by your rocket, you would first need to go to Venus, traveling twice the distance to Saturn, and yet do it all in a fraction of the time that would have been taken by a direct shot? Now, can you think of such a trick to send a spacecraft to Saturn, which is, by the way, 1.5 billion kilometers away? Yes, you heard me right. 1.5 billion kilometers using a rocket just 1/3 of Apollo's mass on a one-way trip lasting less than 7 years. Take several minutes to think it over. You've probably scratched your heads really hard to get that spacecraft to Saturn. If you thought of big rockets, then you were right. However, rockets on their own won't do the trick. A very huge rocket with a huge fuel tank won't be able to lift itself off the ground. First, let's get an overview of where this is heading. This video module will show you how to make gravity help your spacecraft to steer from one planet and send it to another planet. Gravity assist, as this nefarious activity is called, is a maneuver performed by interplanetary spacecraft to travel farther on less fuel. It relies on stealing angular momentum from an orbiting planet. This video module is a classic exercise in Newtonian mechanics. The basics are already present in your high school physics textbook. Linear momentum, to explain rocket propulsion, angular momentum, Newton's law of universal gravitation. Everything will be combined together to produce orbits, and then we will see how gravity assist comes about. It turns out that gravity assist is basically a series of choreographed jumps between planets. Taken separately, you've already seen these topics in your textbooks. However, what we're going to do here is to combine them in new ways that will lead to out-of-this-world results. In particular, after participating in this module, you'll be able to calculate the final velocity of a rocket, calculate periods, energies, angular momenta of planets, explain in your own words how to transfer linear momentum from one marble to another, explain in your own words what gravity assist is, work out specific examples of gravity assists, and explain in your own words to your friends how can a spacecraft launched from Earth reach Saturn faster than on fuel alone. Okay, back to rockets. Let's start from the very beginning. To understand how a rocket works, we'll need to understand what is conservation of linear momentum. As you already know, the linear momentum of a moving object is the product of its mass and velocity. So conservation of linear momentum implies that the total momentum before, initial, must be equal to the total momentum after, final. nice thing about linear momentum is that it is conserved. Actually, that's a law of nature. Being a vector quantity, linear momentum in one direction can cancel linear momentum in the opposite direction. That's what rocket science is based on. To balance the backward linear momentum of the rocket's jet, the rocket must move forward. Starting with a rocket at rest, the backward momentum of the exhaust gas must be balanced by the forward motion of the rocket. That's how the rocket gets its motion. A complication here is that the mass of the rocket is decreasing, but that only means that the equations will get a little bit more difficult. Please note that the speed of the exhaust gas is measured relative to the rocket, that is, from the rocket. I've skipped some algebra here, but those of you who wish to derive the rocket equations can do so. It may take them some time, but it's definitely worth it. Current rockets have exhaust speeds of a few kilometers per second. Fuel consumption rates vary between a few milligrams per second to several tons per second, depending on rocket design and use. For example, rockets that are used to maneuver spacecraft in deep space consume few milligrams per second, whereas rocket boosters used to lift payloads into space, such as satellites, consume several tons per second. Let me show you a couple of examples. Suppose you have a rocket with an exhaust speed of 3 kilometers per second and consumes fuel at a rate of 200 kilograms per second. The achieved thrust would be 600,000 newtons. The maximum mass of a payload that it can lift from Earth's surface is then 600,000 newtons divided by Earth's gravity, which gives us 61 tons. Another example is if you have a rocket whose mass is 3,000 kilograms, of which 2,000 are in fuel. And if the fuel consumption rate is 3 grams per second, V initial is 0, the speed of the exhaust gas is 3 kilometers per second. If you plug all of these numbers in the rocket equation, then the final rocket speed would be 3.3 kilometers per second. The burnout time, the time it would take for the fuel to be completely consumed, would be 2,000 grams divided by the fuel consumption rate, which is 3 grams per second, and that will give you 185 hours. Please note that the final speed of the rocket does not depend on the fuel consumption rate. It depends on the speed of the exhaust gas. I will leave you now for several minutes to practice your rocket science. Enjoy. Hello again. I hope you've enjoyed your first sip of rocket science. As you just calculated, rockets on their own won't get you to Saturn in a timely fashion. We need something else. We need other concepts, namely Newton's law of gravitation and Newton's second law. We need these concepts to understand orbits in the solar system, how the Earth, planets, comets go around the sun. Let us look at Newton's law of universal gravitation. It says that the force of attraction between two masses is the product of the masses divided by the distance squared. Let us look at some graphics here. Newton's law of universal gravitation says that the forces are mutual. I pull on you, you pull on me. The forces lie on the same straight line that joins the two masses and is inversely proportional to the square of the distance. So if you double the distance, the force will decrease by 4. If you triple the distance, the force will decrease by a factor of 9. To get orbits, gravity was one side of the equation. Remember Newton's second law? It said that the force on a mass m will result in an acceleration a. So basically, if we equate the two laws, Newton's law of gravitation and Newton's second law, for the two masses, will give us these two equations, and if we solve them, we will be able to get the motions of the planets. Unfortunately, these equations are too difficult to solve. So instead, we're going to rely on this applet to help us understand orbits. So for example, if the speed of the planet is very small, that is, its energy is small, then the results will be catastrophic. The planet will fall towards the sun. If, on the other hand, the velocity of the planet is very large, then the energy of the planet will allow it to escape from the solar system completely. Only if the velocity of the planet is just so would the planet follow a stable orbit around its star. As a matter of fact, orbits in the solar system are governed by Kepler's 3 laws. The first law says that all planets orbit the sun in ellipses, with the sun being at one focus. The second law says that the speed of the planet along its orbit is variable. It is fastest, the planet is fastest at distance of closest approach, the perihelion, and slowest at the distance of farthest approach, which is the aphelion. The third law says that the square of the period, where the period is the time it takes the planet to complete one orbit around the sun, is equal to the cube of the semi-major axis, which is basically the distance from the center of the ellipse to the perihelion or the aphelion. Before I leave you, I just want to tell you what is the energy of an orbit. It is basically the kinetic energy of the planet plus the potential energy. I will leave you now to practice your orbits. See you. I hope your head isn't spinning. Going round and round introduces a quantity similar to that of linear momentum for motion in a straight line. This quantity is called angular momentum. Angular momentum is similar to linear momentum. It's mass times velocity, but now since we have an orbit, we have to multiply by the radius of the orbit. Angular momentum, like linear momentum, is conserved. It's what makes this possible. A smaller radius will make the speed increase. For more on this, you may wish to see the Blossoms video module of Professor Walter Lewin, Ice Skater's Delight. Just like the spinning ice skaters, the angular momentum of any object, be it a planet, a satellite, etc., is conserved. Actually, the angular momentum of an orbit and its energy are conserved quantities. If you want to go to a different orbit, then you need to change your energy and angular momentum. Okay, so you have your rocket and wish to launch it to Saturn. The first thing you need to realize is that your rocket is in orbit around the Sun. It is initially on Earth. Its angular momentum is related to the orbit it is in. I will leave you to explore this point. You calculated energy and angular momentum of spacecraft on Earth-like orbits and comet-like orbits, and can see that there is a huge difference in their values. Earth-like orbits lead to much lower energy and angular momentum than comet-like orbits. If you started wondering if it's at all possible to somehow get that extra angular momentum, give it to your spacecraft to put it on a comet-like orbit, then you are on the right trajectory. The question now is how to get that extra angular momentum. Let us use an analogy that involves collisions we are all familiar with. We have here a small mass, this will be our spacecraft, and a larger mass, this will be our planet. When the two masses collide with each other, linear momentum will be transferred from the larger mass to the smaller mass. Please remember that the total linear momentum of the whole system is conserved. The momenta of the two masses combined before the collision is equal to the momenta of the two masses combined after the collision. Now, the amount of linear momentum transferred from the planet to the spacecraft is negligible with respect to the planet, but a lot with respect to the spacecraft, owing to the spacecraft's low mass. That implies that the velocity of the spacecraft after the collision will be a lot larger compared to its velocity before you started. By how much? Let us look at the equations of this system. Before the collision, this is the total linear momentum of the two masses. This is the linear momentum conservation equation. And this is the total linear momentum of the system after the collision, momentum of the small mass, momentum of the larger mass. Energy conservation equations, kinetic energy of the smaller mass plus the kinetic energy of the larger mass initially is equal to the kinetic energy of the smaller mass plus the kinetic energy of the larger mass. After pretty messy algebra, one gets the following. You may wish to derive these equations if you want. We will get the final velocity of the smaller mass. It's this equation. Now, what is important about this is that if the mass of the planet is a lot larger than the mass of the spacecraft, which is the case, then the velocity of the spacecraft after the interaction is equal to the velocity of the spacecraft before the interaction plus twice the velocity of the planet. That's why the velocity of the spacecraft after the collision is a lot larger than the velocity of the spacecraft before the collision. Hello again. I hope you had fun getting marbles and balls steal linear momentum. Let's now try our hand at making spacecraft steal angular momentum from moving planets. As you probably recall, planets go around the sun in ellipses with the sun at one focus. The point of closest approach is called the perihelion, while the most distant point on the orbit is called aphelion. Now, when the spacecraft is still here on Earth, on the launch pad, actually it's in orbit around the sun. The rockets that you see huff and puff are used to oppose gravity to place our spacecraft in orbit around Earth. Once in orbit around Earth, gravity becomes your secret accomplice. It can take your spacecraft to places not possible on your limited fuel budget. Let's say you want to get a gravity assist from Jupiter. This is the Sun, Earth, and Jupiter. To get a gravity assist from Jupiter, you need to get there in the first place. To do that, you'll want to increase your energy to transfer from an Earth orbit to a Jupiter orbit. To do that, you basically need to put your spacecraft on a new orbit, this green ellipse, whose periapsis, point closest to the Sun, similar to perihelion, is at Earth's orbit, and apapsis, similar to aphelion, point most distant from the Sun at Jupiter's orbit. You have calculated in previous segments the energy associated with a given orbit. To increase the energy, you need to fire up the engines of your spacecraft to accelerate it in the direction of Earth's orbit around the Sun. For a short while, that will give you just the right amount of energy to transfer to the new orbit. Getting to Jupiter won't necessarily mean that your spacecraft will automatically get a gravity assist to fling it to the outer parts of the solar system. To get a gravity assist from Jupiter or steal angular momentum from it, the spacecraft must approach, well, you've guessed it, must approach Jupiter from the back. So to get a gravity assist from Jupiter, your transfer trajectory must be carefully planned so that the spacecraft approaches Jupiter from behind. We have here 3 trajectories. One of them is a gravity assist trajectory. Let's play it again to see which one. The blue spacecraft, follow the blue spacecraft. It's approaching Jupiter from the back. It's the point of closest approach to Jupiter is from the back when Jupiter is moving in that direction. So that spacecraft will get the maximum kick compared to the other trajectories. The trick is to sneak up on the moving planet from behind. This is the planet, this is the moving planet, this is the spacecraft. It is approaching the moving planet from behind. This way, the spacecraft will be able to steal a little bit of angular momentum without the planet even noticing it. This is because the mass of the planet is a lot larger than the mass of the spacecraft. The result of this angular momentum stealing would lead to the increase in the speed of the spacecraft. One can see this from the following simple diagram. This is the initial velocity of the spacecraft. This is the velocity of the planet. And from simple geometry alone, one can easily see that the final velocity of the spacecraft a little bit larger than the initial velocity of the spacecraft. The situation here is similar to the collisions you played with in the last segment. The collision is transferring angular momentum from the moving planet to the spacecraft. The collision is mediated through gravity. If the planet is not moving, then there's no angular momentum to steal, and the collision will simply change the spacecraft's trajectory. Think of a basketball bouncing off a stationary wall. The wall will simply change the direction of the ball without changing its speed. Now, can you think of why the spacecraft must approach the moving planet from the back and not from the front? I'm back. The answer is simple. In the marbles example, momentum transfer occurred through a repulsive collision. In the case of gravity, it is attractive. So to transfer momentum from the moving planet to the spacecraft must approach the planet from the back. Spacecraft can get gravity assists from, in principle, any planet. However, if the planet is too small or too slow, then it is useless. For example, the Cassini-Huygens mission to Saturn was on what is called a VVE-GJ trajectory, a Venus, Earth, Jupiter gravity assist. It got 2 gravity assists from Venus, 1 from Earth, and a final one from Jupiter. To get to Venus, the spacecraft rockets were fired up to slow down the spacecraft, thus make it transfer to an orbit whose periapsis is at Venus and apapsis is at Earth. Just to impress your friends later with big words, these kinds of transfers are called Hochmann transfers. I bet that you are already familiar with angular momentum transfers without even knowing it. If you have ever played tennis, table tennis, baseball, or badminton, birdie and racket, then you have transferred angular momentum from the swinging racket to the birdie. As you can see, angular momentum is transferred from the swinging racket to the birdie. The faster the racket, the larger the angular momentum, and hence the contact interaction will transfer more angular momentum to the birdie, making it go faster and farther. Of course, we have a repulsive interaction, so the birdie must come from the front. Now, if you'll excuse me, I wish to continue my game. Our journey was long but very rewarding. We were on a trajectory that got us into linear and angular momentum, energy, Newton's second law, gravitation, and orbits. Stuff mostly in your physics textbooks. Rocket science is actually a testimony to the law of conservation of linear momentum. We combined different parts of classical mechanics to come up with orbits. We found that every orbit is associated with a given energy and angular momentum. To change orbits, all you need to do is to change your energy and angular momentum. Small rocket bursts, if carefully timed, can take you to a planet, sneak from behind it, steal angular momentum from it, and get away. Gravity will assist you in this. Gravity assists are simply carefully choreographed jumps between orbits. I hope you found this module fun. It was really fun preparing. Over and out. The purpose of this video module is to explain how to send a spacecraft to the outer solar system on a limited budget of rocket fuel. It turns out to be relatively easy to achieve and also to understand with basic Newtonian mechanics. This video module will present gravity assist, or what is wrongly referred to as the gravitational slingshot. Gravity assist is a maneuver performed by interplanetary spacecraft to travel farther on less fuel. It is a classic exercise in Newtonian mechanics. The basics are covered in high school physics curricula. Conservation of linear momentum to explain rocket propulsion, angular momentum, Newton's law of universal gravitation, and energy conservation. These concepts will be combined to explain orbits in the solar system. Gravity assists turn out to be carefully choreographed jumps between orbits. Only a single topic needed is usually not covered in high school curricula: distances in the solar system. A quick introduction into distances in the solar system will be enough to put the problem of fuel constraints in interplanetary travel into perspective, and also to later highlight the importance of gravity assists in solving this fundamental problem. In short, gravity assist will integrate many seemingly separate parts of high school Newtonian mechanics to present and explain a real application. Gravity assist will touch upon many exciting topics: rocketry, interplanetary travel, the solar system, etc. The most striking aspect of it will be to show that these topics can be understood using only high school physics, hence demonstrating the importance of physics in serving humanity's thirst for space exploration. The proposed video module is a new way of looking at and applying various concepts of Newtonian mechanics studied in high school physics, extends the theory studied in the classroom, and a real-world application to a very real problem, that of exploring the solar system. Your students should have a working knowledge of all the above concepts. The best time to show this module is at the end of the mechanics part. You may wish to show in your class first, though it is not essential, MIT Blossom's video modules of Walter Lewin, Ice Skater's Delight, and Pervez Hoodboy's The Mystery of Motion. You can find a duet-by-duet teacher's guide.
you.